Welcome back.
Hello and welcome back to Calculus 2, which is now going to turn into a preview of Calculus 3. So parametric equations are going to be the heart of a lot of stuff in Calc 3. 2 chapters will depend on this, and this will show up on your final exam. So we have a new method or a new lens to look at functions through parametric equations. So let me first say that in a nutshell, what parametric equations do is they break dimensions into separate equations and then do so in terms of a parameter. So if I have a function y equal f of x, or if I have an implicit function f of x y equal to 0, right? What parametric equations do is they take this and they break dimensions. X equals g of some, let's say, parameter t, and y equals h of some parameter t. And they would do the same thing for formulas that are not functions and create x equals g of t and y equals h of t. So this is what parametric equations do. They break dimension x away from dimension y. Each one of those gets its own function. But if you get to put them together, you will actually get your original equation. And this is actually extremely powerful and very useful because it allows us to work with equations that are not functions. In calculus, you know that you like to differentiate and integrate functions. Now, the non-functions also can be integrated or differentiated, but you have to use special things, right? Like implicit differentiation to differentiate a circle. So now what I'm going to do is I'm going to take these dimensions and I separate these with functions. Now, the introductory example is not something that you are actually using parametric equations for, because it is better if you actually use the function that you have. But it's a good way to illustrate what we are talking about. So y equals x squared plus 1. So you have a very familiar function, y equals x squared plus 1. It's a parabola. And the most trivial way to obtain parametric equation, the set of parametric equations for something like this, is to define that x is equal to t, in which case y would be t squared plus 1. Now, you haven't achieved anything. You actually made it worse, because y equals t squared plus 1 is the same as y equals x squared plus 1. So, and you just have an extra equation floating about. So you actually made it worse in this case. But I just wanted to show that you have a function that is given in terms of x and a y, which is what you used to so far, and then you have one of its parametric representations below. Now, these two work differently. When you graph your x squared, right, you will have a parabola. You draw the parabola and you're done. Now, for set of parametric equations, the way you graphed the parabola was you pick x's. So you pick x's and you compute y's. Now, when you are dealing with parametric equations, you will pick t's and you will compute x and the y. So this is what you pick, and these two are what you compute. Now, you can think of parameter t as time. So I can go and I can pick, let's say, -2, -1, 0, 1, and 2, and this is -2 seconds, -1 seconds, 0, 1, and 2 seconds. And now, being that x is equal to t, right? So we have negative 2, negative 1, 0, 1, and 2. As I said, this example is not the greatest, but it just brings the calculations across. When I square all of these and add 1, I get 5, I get 2, I get 1, I get 2, I get 5. And now, we get the same graph as we had before. You graph your 0, 1, negative 1, 2, and 1 and 2, and then it's 2, 3, 4, 5, here and here, and you hit the line through this. Oh, I should have graphed this way because it goes through 1. So it's the same graph, as you can see. We get the same graph, but we actually have more information when we do parametric equations than when we do the regular graph, because parametric equations bring in now the orientation. See, we have a motion over here. We have motion described because the time flows from negative t to positive t. So this is your first point, t equals negative 2 seconds, and then t equals negative 1, and then t equals to 0, t equals to 1, and t equals to 2. So I connected all of these points from left to right, and we see also that now all of these parametric curves are oriented, right? And they will be going clockwise or counterclockwise being the default. So this is what parametric equations are. Now, again, you are not using parametric equations to work with parabolas and things that are nice and easy. You are using parametric equations to make easy stuff that it's hard and the calculus can't deal with, like circle. Now, this is where you have to memorize what the parametric equations look like for a circle. So we start over here with saying, like, let's take a look at a circle. Equation x squared plus y squared equals to 9. We know this is a circle of radius 3. So, circle, radius 3. We know that circle is not a function, therefore we have to use implicit differentiation to differentiate, and we have to use a lot of mathematical gymnastics to actually integrate. Right? You have to do the integration of 1/4 of this and use the trig sub in there and then do the rest. Now let's see what kind of joke parametric equations make of this. Parametric equations for a circle, and this is me telling you what they are, is 3 cosine t and y equal 3 sine t. They work as a pair, so I put this brace to kind of push them together. So here's your parametric set. Now, if you look at this parametric set, aren't these just a very basic, easy functions to work with, sine and cosine, right? So this is what parametric equations do for us, right? They take something that was not even a function and write it down as a set of functions that we can work with. So now when you're looking at this circle, we also see that there will be a counterclockwise motion as t grows from 0 to 2 pi. So let's try this. When t is equal to 0, x is 3 and y is 0. Well, that's this point here. So t equals 0 is there. T equals pi over 2. T equals pi. T equals 3 pi over 2. And finally going back to t equals 2 pi. So we see that for time to go from 0 to 2 pi, we get to trace the entire circle, and that was done counterclockwise because the time increases. Now, guys, 2 pi is roughly 6, let's say 6 seconds or 6 minutes or 6 hours or 6 years, whatever. So the time grows from 0 to 2 pi, roughly saying time grows from 0 to 6.28, right? So we have a circle, and then the other 2D shape that is generally issued is ellipse. An ellipse has an equation x squared over a squared plus y squared over b squared equals to 1. And when you draw an ellipse, you have major radius A and then this minor radius B, the way I have the equation written over there. Parametric set for this is x equals A cosine t, y equals b sine t. And there's your ellipse. Now, one of the skills is to figure out how to get these equations back into our form, how to combine. Because if I give you a set of parametric equations, maybe you want to know what was the original equation. So say that I have, so convert to xy equation. And I am given set of parametric equations. X equals, let's go with 6 cosine theta, or t, let's go with t. And y is 6 sine t. So the way we do this is we solve one of these for t and plug into the other one. So t is the inverse sine of y over 6. And then we plug in. So now I have that x is equal to 6 times cosine, and instead of t, I have inverse sine of y over 6. You remember these problems from pre-calculus 2? They were completely pointless, right? When you had to do tangent of inverse secant and sine of inverse cosine. They had zero application in your pre-calculus 2 course. It was just an annoyance that you had to go through to pass on a test. Well, there it is, showing up right now for the first time, right? Being useful. So the way we solve this is we draw a triangle on a side. Say that's angle theta there. Sine is opposite over hypotenuse, so this is y and this is 6, making this 36 minus y squared for the hypotenuse, for the adjacent, when you use Pythagorean theorem. So now you get to rewrite this thing 6 cosine, and instead of sine inverse, you are doing cosine inverse, but cosine is adjacent, which is the square root of 36 minus y squared, divided by hypotenuse, which is 6. And now cosines die. That's why we did the transformation there. So what you have is the 6 times the square root of 36 minus y squared over 6, and this is where 6's die, giving us equation that x is equal to square root of 36 minus y squared. So that's x squared is equal to 36 minus y squared. Move the y squared on the other side, and we all get what you were expecting to get, circle with radius 6. When the parametric equations have the same number here, it's the circle. When it has a different number here, it's an ellipse. So our problem had 6 and a 6, so it's a circle. Now clearly this calculation, you're not going to be doing this calculation every time because you're just going to know parametrization for a circle. So you'll just go from there. So we just shown how to get from this to, right. Now what's next? Well, parametric equations are very powerful. They work in any number of dimensions. So you are going to use the parametric equations in Calculus 3 a lot to show space curves and vector valued functions and all of these kind of things. And then chapter 14, which finally started with line integrals and everything else. So parametric equations are used later a lot. Make sure you understand this. Now, we know that we have a circle. I won't talk about derivatives now. We know we have a circle with, in our case, was radius 6. And I know that at any given point for this circle, I can find the tangent line for that circle. Now that means that there is a derivative that we can work out for this. And this is the awesome part. I have my x defined to be g of t, and I have y to be some function h of t. This is what our definition for parametric set is. I don't care whether it's a circle or whatever it is. I took the circle. So now in our case, this would be 6 cosine t and 6 sine t. What is dy dx? Well, if you think about the derivative dy dx, wouldn't that just be dy dt divided by dx dt? Because simply by multiplying by dt top and bottom, which is actually 1, right? Because dt over dt is 1, you will just get dy over dx. So this is your formula. It's h prime of t divided by g prime of t. Just have to be very careful to flip it, guys, because in a derivative y is on top, and when we do the parametric set, y is on the bottom. So a lot of grades go down the drain if you don't flip it. So y, and y is connected to h. So h. So now if I want to find the derivative of the circle, yeah, we can go use implicit differentiation, but we can also find the differentiation here as dy dx is equal to, and now the derivative of h, right, h prime, so that's 6 cosine t divided by negative 6 sine t, which is equal to negative cotangent t. That's the derivative of the circle. So now you give me the value t at which want you to compute your tangent line. I will give you the slope of the tangent line, because the slope m is, in this case, negative cosine t, sorry, negative cotangent t, computed at t equals to some value t0 at which you want to figure out. Or let's put a, whatever. So you can find tangent lines, you can find everything using this form. So I did it for the circle. got the derivative, so that's the derivative, and now I just need to plug in t to calculate the slope. So I would like you to find one of the tangent lines, and we're done. I just have to go get the equation. All right. So here we go. X equals 16 sine cubed t. And y equals 13 cosine t minus 5 cosine 2t minus 2 cosine 3t, and finally minus cosine 4t. Let's get the tangent line at, let's say, t equals pi over 4. Or actually 0. Let's go t equals 0. That's the easiest. Whatever. So your job is to find the derivative and then figure out the rest. I'll give you a few minutes.
Some of the exams will, or it's not on the test, just on the exam.
All done? I hope you're done. So I'm going to find the derivative of y first, because it's y divided by x. I don't want to mess up. Derivative of 13 cosine t, negative 13 sine t, and then I have, again, cosines. So all of these are cosines, so they're all going to be negative signs. So plus 10 sine 2t minus plus 6 sine 3t plus 4 sine 4t, and then x prime is equal to 48 sine squared t times cosine t. So that's that. So my derivative dy dx is going to be the whole thing up there with the negative 13 sine t plus 10 cosine t, no, plus 10 sine 2t plus 6 sine 3t plus 4 sine 4t, everything divided by 48 sine squared t cosine t. Oh, t equals 0 is a bad value. I see. Okay, let's go pi over 4. I wanted pi over 4 originally, but then I switched. I don't know why. Yeah. So if I do pi over 4, we can calculate slope because it's negative 13 square root of 2 over 2 plus 10 plus 6 of 3 pi over 4, that's a root 2 over 2, plus 4 pi over 4, 0, so that's a 0, divided by, on the bottom, I have 48 times sine of pi over root over 2, so that's 1/2, and then root 2 over 2. So now, I have negative 13, so that's negative 7 root 2 over 2, plus 10, so that's 20 minus 7 root 2. Everything divided by, this will actually cancel, and I have root 2, this is 4, 48, 12. So now this becomes, slope is 20 minus 7 root 2 divided by 24 root 2. We multiply by root 2. 20 root 2 minus 14 divided by, again, 48. Divide by 2 everywhere. 10 root 2 minus 7 over 24. So there's a slope. M equals 10 root 2 minus 7 over 24. Now the point is going to be when we take our pi over 4 and plug into equation for x and equation for y to find the point at which it is. So point is going to be given as we had 16 sine cubed of pi over 4. Well, I can just compute everything at once, so I don't have to write it 15 times. Pi over 4, so that's root 2 over 2 cubed, comma, and now we have the long, so that's 13 root 2 over 2 minus 5 cosine 2t. So that's going to be cosine of pi over 2, that's a 0, minus, then we have, the next one is 3t, right? sine 3t, that's a 3 root t, that's a negative, so minus 6. And then we have a 4 sine of 4t, so sine is 4t times, that's 2 pi, so that's 0. So another 0 there. So our point at which we are calculating this is going to be, that's 8, so 2, 4 root 2, comma, and this minus 6, that's a 12, so 13 root 2 minus 12 over 2. Y equal mx plus b. Your y is 13 root 2 minus 12 over 2 is equal to slope 10 root 2 minus 7 over 24 times x, which is 4 root 2 plus b. And this is what calculates our b. So 4 and this will cancel. We get a 6. Root 2 will multiply on top. So 13 root 2 minus 12 over 2 is equal to 10 root 2, that's 20, minus 7 root 2 divided by 6 plus b. So b is, now I need to multiply that by 3. 39 root 2 minus 36 over 6 minus 20 plus 7 root 2. There we go. Over 6. And finally, b is equal to 39 plus 7 is 46 root 2. Minus 56 divided by 6. And that cancels by 2. Gives us 23 root 2 minus 56. That's 28. Divided by 3. That's 10, that's 5, that doesn't work. Great. So now I have that y is equal to, the slope was given as, what? 10 root 2 minus 7 over, what? 24. X plus 23 root 2 minus 28 over 3. So that's our equation.
I had that.
You had that, right? So why? So you can be cool.
Exactly.
Hold on. Haven't seen the graph yet.
He was playing it this whole time.
Is that for me?
Cute.
These are your parametric equations.
How lovely. Is that why we took the break for you to make this?
Yeah. So parametric equations, here is the set of parametric equations that we just worked on, entered in Desmos. And now if I am to go and work out these in decimals and type this in, you'll be having a tangent line that would come in like this over here.
We have to bake the chicken? They missed the heart.
What?
Is that a new cup? Split the heart in half, so it's still like...
You had another different cup every now and then.
Yeah.
3D printed that.
Every time. Yeah, 3D printed this cup.
I just want to know why you gotta do another chicken. That's the real question. Look at the actual math. Like, what are the season this bad boy? My brain is wrong. Should have left.
Maybe doesn't believe it.
See you all.